We are taking donations. I was expecting a smaller crowd, so I'm very grateful to be proven wrong. I hope you all enjoyed the speaker today.
Thank you, Kendall. Welcome. It's not Armageddon, but it's over there, right? So I'm kind of surprised people came out against the herd of people who were going that way to get out of here. Anyway, hopefully the fire danger passes. Let's see. So I'm going to give a history of the whole planet, and then eventually end up talking about the rocks around here. So I'm going to go global, and then I'm going to go regional, and then I'm going to go Duluth to Thunder Bay, and then I'm going to go Grand Marais to here, ending here, and why the rocks here are interesting. So I've had the pleasure of 40 years of my life being some form of a geologist, one way or the other. And who's the best geologist? Well, the person that sees all the rocks, right? And so when you look at the planet, there's sort of two ways to look at it. Everything that is underlying an ocean is basalt, and it's really boring. You wouldn't believe the number of tax dollars that have been spent by the U.S. government to drill holes in the ocean floor to find out that it's the exact same rock everywhere you go. There's some other good tectonic things and global history things that come out of that. So continental crust, on the other hand, is very interesting, very diverse, lots of different ages, lots of different processes, lots of diversity of things. So 70% of the surface of the Earth is kind of dull, the other 30% is kind of interesting, but it's also really thick. So 30, 40, 50, 60 kilometers deep is what continental crust is. There's a lot of variety in all of that. So anyway, I've had the pleasure again of being able to get to all the continents, research projects on all the continents with my students, and that makes me, I think, a better geologist than a guy that sits in an office and looks at a computer screen all day. So geology, for most people, when you're getting into it, it's about getting out and being outdoors. So that's probably most of you, because you're either visiting or living out here and getting outside. Outside's always better than inside. And so I will show you a variety of members of my family as we go through this. We just got rid of child number 3 a few days ago, a week ago. She did a geology degree, but she's really a chemist. Now her life is going to be inside, in a lab, in a room, all by herself, quiet and dark and boring. But she might split the atom or something interesting doing that. So anyway, I grew up with a father geologist who also traveled the world and sort of got me interested in the global aspects of understanding Earth processes and so forth. So I've tried to do my best going forward. So let me just say a few things about geologists and then this cheesy title that I put up here. Geologists are kind of a bipolar group. So we want you to be aware of the antiquity of the Earth, 4.6 billion years old. At the same time, we want you to not live on a plate boundary because you might die from an earthquake. Right? So we could talk about Haiti. It has a horrible political social history, but it's an island on a plate boundary. Well, don't live there. That's the geologist's view of that. How about the Pacific Rim? Everywhere around the rim of the Pacific Ocean, you have subduction systems, active earthquakes, active volcanoes. Don't live there. And so where do we end up? At least some of us. It's kind of let's see the live anyway. So if you live in the middle of a continent where the rocks are really old and thick, nothing ever happens except when we have fire. Or you might not like being here because we have 6 to 8 months of winter, which we happen to like because the skiing's fabulous, except last winter when we didn't get any snow. Anyway, so the title here, I went long on the its and ites, so let me just say a few things about those words. So a tonalite is the rock you happen to be sitting on under the building. Out here it's called the sag tonalite, because nobody can pronounce that whole word that is sag. You just say sag and all that other stuff. All right. So the sag tonalite is what underlies a good part of the area here in an Archean terrain, which you'll see again is a sort of greenish area. These are rocks that are 2.5 billion years or older. Lots of big blobs of granite-like rocks, and also those which are tonalites. So a tonalite is a rock to most people looks like a granite, but it's gray. It's missing a pink mineral called potassium feldspar. It's probably the most common rock on the planet, at least in continental crust, if we ignore all that basalt in the oceans. So tonalites are part of the story. Diamictites are glacial deposits that have been lithified. So we've had probably something like 5 glacial episodes, big cooling events over Earth history that we know of. I found some evidence west of here, 10 or 20 miles, to suggest that there might be yet another glacial epoch that is preserved in some of the sediments out there. So diamictite is a type of sedimentary rock. It often has evidence for glacial deposition. So we'll talk about that a little bit. And then I'm mixing my ites here because Tillite, there's lots of glacial goodies around here that are last week's deposits. So the Pleistocene ice age started 2.4 billion years ago. We're still in it. We still have ice caps and valley glaciers in various places. So there's some nice glacial deposits around here. And I'll show you some pictures of those out here on the Gunflint Trail. And then seismites, that's sort of a new word in the geology literature. So we'll talk about the Sudbury impact event, which happened 1.85 billion years ago near Sudbury, Ontario. But you can find rocks around here, about 800 kilometers away, from that impact event that are deposited as breccia deposits. So it's ripping up the banded iron formations that were being deposited globally in ocean basins, and then one day all that stopped. So a seismite is a very unique type of sedimentary deposit that in most cases is related to an impact event. So let me see if I can do this. Can I go? Nope. So next slide. Okay. I'm going to go off of this slide a bit because it's really annoying to look at. So the word you want to have in your vocabulary now is geoid, not geode, geoid. We'll talk about geoids, which around here are also called agates. So that's completely separate. So if you look at the Earth spinning around, you can probably identify the continents, the oceans, and the colors indicate highs and lows. So the Earth is an oblate spheroid, so not a sphere, but it's flattened at the poles. So the equatorial radius of the planet is 21 kilometers shorter, the polar radius is 21 kilometers shorter than the equatorial radius. What does that tell you about the planet? Well, it's kind of squishy, right? It's got some soft stuff in the middle. The mantle flows into squishy. There are liquids in the outer core and so forth. And so the manifestation of motions in the interior of the planet relative to plate boundary interactions, mostly subduction zones, gives you this lumpy thing. So what's your favorite vegetable? Looks like a potato, right? Okay, so next slide. So here's 3D flattened out to 2D. That's a little easier to look at and less annoying with the squiggly thing. So the deviations from that oblate spheroidal shape are, tens, maybe 100 meters. These are third order variations on the surface morphology of the planet. They represent things going on interior to the planet because that's the mass of the planet. The crust is either 8 kilometers thick in the ocean basins or up to 40 or 50 in continental crust, and that's a 70-30 split. So what you should worry about is what is this big blue low? So that's an innie, right? Superimposed on an oblate spheroid. So that's a low. That's India subducting underneath Asia. The result is the Himalayas. And who's winning? Asia's winning, India's losing. And the net result is you have an innie. Next door, you have an outie. So it's a high, right? The red colors are highs. So innies and outies. And the way you get students to remember this is by having them think about the next slide. Innies and outies, right? They all have a beer gut in some form, right? And so innies and outies are third order, low amplitude, long wavelength deviations on the oblate spheroid. Okay? So now you're all happy with your planet, so let's keep doing global stuff. The next few slides are 2D representations of all the different plates. So you happen to be sitting somewhere in North America. This plate is moving 2 centimeters to the west-southwest every year. We measure that using GPS methods and other fancy techniques. And if you do enough global GPS things and enough fancy technique things, you can then delineate nicely where all the plate boundaries are. So things like mid-ocean spreading ridges are easily defined with ocean bathymetry and other things. Continents are more complicated, and again, excuse me, it's worse with the microphone, sorry. So lots of different plates, and we keep better defining the subplates or microplates by better seismology arrangements, better GPS measurements of all kinds of things. So instead of a couple of big plates and a couple of little plates, it gets more and more complicated. And then these crosshatch patterns are, when people do computational things, the new Bell models in the literature, you find mismatches of plate velocities, both vertical and horizontal, and it's sometimes messy. So the messiest place, of course, is Asia, where India is colliding into Asia, and you have a big subduction system. So anyway, the next slide is a similar global representation of different plate boundary types. And so we have shaded areas which are mismatches, but for instance, in the Atlantic Ocean, this is the Mid-Atlantic Ridge. And so you have divergent plate motion here, the passive margin on the west side of the Atlantic Ocean. You go to the other sides of the Americas, everything is subduction or transform boundaries. Oceanic crust is going beneath, you're forming mountain chains, lots of seismicity, a very dynamic place to live. But we don't understand this fully, and then when you think of tectonics, we know plates move, but we have no idea how or why. So that's still the $38 question. What makes these plates move? And it's still kind of a mystery. All right, next slide. So, sorry. I put this in not to be a climate change guy one way or the other, and my bride is giving me a drink. Thank you. She won't be so nice later when I show a picture of her. So, climate change. Well, you have to think about ocean circulation, atmospheric circulation, and this image gets you to think about the normal year, La Nina, versus the abnormal year, El Nino. So during an El Nino year, you don't have an upwelling of cold, nutrient-rich waters in the Humboldt Current. The fishery dies off, and all that warm equatorial water moves east instead of the normal year where it moves west. You have the monsoon, rains get to Australia, get to Eastern Africa, and so forth. So the word to remember is isthmus, which I can't pronounce at all. So the isthmus that disconnected the southern tip of South America from the Antarctic Peninsula happened a million years ago. And what was the result of that? You isolated Antarctica, you have the circumantarctic current, and you form a polar ice cap. It's been there for 35 million years. If you run the movie forward, what do you get? Start of the Pleistocene Ice Age, 35 million years ago. So it's a big tectonic event that results in an oceanographic and atmospheric event. The other isthmus, which is a connecting isthmus, was the connection between Central America, North America, to South America. So what happens when you block the equatorial oceans in that region? You isolate the Atlantic from the Pacific, and you get El Nino or La Nina. That happened 5 million years ago. Okay? So that tectonic event set up an oceanographic and atmospheric event, which then affects all kinds of things, including with the normal year, the monsoons moving west. What happens in East Africa 5 million years ago? Somebody climbed down out of a tree and started walking. Humans evolved, right? So you can argue that that's related to a tectonic event. All right, next slide. Okay, so Sumatra 2003. What happened there? Subduction along that particular yellow line, the subduction zone. Big earthquake, magnitude 9.3, the biggest one we've ever measured as humans with our instrumentation. And what did you get? Huge tsunami event. I'll show you the movie of that in a minute. 250,000 people died. So the earthquake happened in this neighborhood, subduction underneath the crust here, motion that way, there are volcanoes along here. And the head waves from the tsunami went this way and that way. And they propagated the whole planet. So the next slide is a movie, which I'm thinking, if you can move the cursor somewhere, you'll get a way to turn them, yeah, you can make the movie go. So the action, oops, this isn't going to run. Bummer.
Exit the PowerPoint.
Yeah.
Press the escape button. Oh yeah. Yeah, now.
So it should run as a movie. Well, so the punchline is giant earthquake, offset of the ocean floor, which offsets the column of water, and you get a head wave that goes this way, huge damage along the Thai coast, and then this wave goes out. It's moving 500 miles an hour, and it's not one wave, but 10. And these waves propagate all the way around the planet. I think it's 36 hours later, you get a head wave coming into New York Harbor. So this is the first time we had instrumentation to be able to monitor something like this. So we monitor it seismically, and then we monitor, in this case, using all kinds of satellites, this wave motion across the whole ocean. So one earthquake that lasted a minute and a half shook the whole planet, made a seismic and oceanographic event that went on, well, actually for a number of days. Absolutely amazing. So you don't like that to happen again, but again, as we get better at monitoring the planet, you get these crazy things that happen like that. So, all right, so I'm going to go through a number of other places that I think most people are familiar with and talk about them. So the next slide, Kendall. All right, Yellowstone. Biz is not here. All right, she's going there in a few weeks, one of my neighbors. Okay, so you've been to Yellowstone. It's an absolutely fabulously beautiful place. And the whole park is the caldera. So when you're in there, the whole thing is the volcano, right? You're going to Old Faithful, the bubbling mud pots over here, Yellowstone Lake. Everything is the caldera. And the whole thing is going to blow up one of these days, all right? So the question is, where are you going to be? So I've worked out in this part of the world for 30-some years and so forth. Beautiful place, horrible to go through because it's full of tourists. And it's also full of bison and elk and bears. So you don't go through there very quickly. Anyway, most people go there and they think, oh, what a beautiful place, and then a 10,000-foot high plateau, and there's all this interesting geothermally stuff, and the whole thing is the caldera. So when did it last erupt? 2.1 million years ago, 1.4 million years ago, 700,000 years ago. What's the pattern? Every 700,000 years, plus or minus what? So there's radiometric dating, and so there's some big uncertainties there, not that big. So 700,000, we're ready to go, right? So where's Biz? She just came in. So Biz is going to Yellowstone. It might erupt next week. Maybe that's a bad thing. So my fantasy is what? I'm in my recliner. The Wild just won the Stanley Cup. I'm incredibly happy. And then this thing can erupt, and it can launch 5,000 RVs into outer space. I can die. May not happen. All right. So the next slide shows you another way to think about Yellowstone. So all of these dots, there's the reds and blues. Every one of these is an earthquake over a relatively short time period. Does that worry you? Well, there's earthquakes and then there's earthquakes. So there are earthquakes that are related to fault motions. And those are very different and interesting to study. There are earthquakes related to detonations of things, and those have a very specific waveform. And these are all earthquakes related to magmatic motion in the ground. So underneath Yellowstone is what we call a hotspot. It's a plume of magmatic material that goes from, let's say, 100 kilometers down, maybe 200 kilometers down. It's a plume that comes out vertically and causes magmatic activity. So this is a scary place. Is it monitored? So you can go online. There's all kinds of monitors on this. So there are seismic monitors, discharge gas monitors, GPS studies, and all kinds of things. So this is the Cadillac of our national parks and one of the most beautiful places on Earth. But it's also a place that if it erupts, does that change the planet? Enormously. It's an enormous change. So the last eruption, you could document 3 meters of ash in Atlanta, plus its global distribution of this discharge. So this is the mother of all volcanoes. This is the 100 out of 100. We're going to look at some wimpy ones in a minute here. So anyway, Yellowstone. So again, I've given you my fantasy. Go ahead, Kendall. So we're over there at the end of the green line. So North America is moving this way, the arrow, 2 centimeters per year, west-southwest. So 2 centimeters, I figured out how far it is from Poplar Lake to here. And how long is it going to take for North America to move to the west-southwest so that my recliner is over the hot spot? 70 million years. I'm not going to live that long. So probably my kids should sell the cabin before then to get out. All right. So this is the path of North America. So if you wanted to buy real estate, where shouldn't you buy it? Don't buy it on the east side of Yellowstone, right? Because eventually the plate's going to move west-southwest. The hotspot doesn't move. So buy real estate over here. Idaho's a good place, right? Okay. Next slide. Seismicity. Here's just a generic view of earthquakes in North America. What's the good news? You're in the middle of a big, slow, thick continent. Nothing ever happens, right? What if you live on the coast? Lots of stuff happens. Why does everybody move to California? We moved to California, but we also moved away quickly. We lived in the Bay Area for a little while. So the punchline again is, don't live near a subduction zone. If you live in the middle of the continent, nice and stable. Next slide. Okay, so let's get a little more local, at least in terms of glacial things. We'll come back to Pleistocene glacial stuff in a little while. These are a little bit confusing. Probably the figure on the left is a better one to look at. So if you do a GPS study of greater North America, what do you find when you look at the vertical signal? So North America is moving 2 centimeters west-southwest every year. But what kind of uplift rates have you got? Huge ones, right? Millimeters per year, sometimes 10, 20, 30 millimeters per year. Why? Well, we used to have 10,000 feet of ice sitting here. And when did it disappear? To a geologist last week. Right? It's thousands of years ago, but not that long ago. So if you put a huge mass of ice here and it melts over a relatively short amount of time, what happens? Again, you're back to an innie. The crust is depressed and it wants to equilibrate, so it's coming up. So the Hudson Bay area is coming up relative to south of what's called the zero line, which is going down. So we're going to talk about how that plays out with the Great Lakes in a little bit. So post-glacial rebound here. Go ahead. No, the next slide just reiterates the previous one. So here's another way of contouring and colorizing rebound rates. And so the rebound rates are really, really high where there was a really thick pile of ice. And so as time goes forward, hundreds of years, thousands of years, you'll eventually get to an equilibrium where drainages will kind of do the right thing. They won't flow in funny directions. And this has an impact on the Great Lakes, right? So Lake Superior, Michigan, Huron, Erie, and Ontario. And this rebound still has an effect on shorelines around the Great Lakes. It has an effect on drainage systems around the Great Lakes. And we'll look at some pictures of some of those things around, at least along the North Shore. All right, next slide. So who remembers St. Helens? So this is also sort of a landmark eruption event for a couple of reasons. So this is one of the volcanoes along the subduction zones on the west coast of the U.S. This is a fairly modest-sized volcano. But again, we had enough observations of this to realize, oh, these don't all do the same thing. So you think of a volcano, this conical shape, once it gets instability, it erupts the plume up, and then it's sort of over maybe a week or a month or a year. This one did something completely different. It started to erupt, and then it collapsed on the northwest side, and the eruption went sideways. Right, so most of you remember that? That was a very unique eruption. So it blew up sideways, and this is kind of looking down the throat of that eruption, and then once that instability played out, then it erupted vertically. So on a scale of 1 to 100, what do you give this one? I give it a 1. All right, so Yellowstone's 100, this is a 1. The next slide gives you another recent volcanic eruption. Some of you might remember this one, Pinatubo in the Philippines. This was maybe a 10 out of 100. And so the eruption here was almost entirely vertical. The chemistry of this eruption was unique because once it played out and the gas and emissions were monitored, it turns out to be a very sulfur-rich plume. So sulfates in the upper atmosphere at a low latitude, what does that do for you? It cools the planet for 5 years. So if you don't like global warming and you want to cool it off for a while, well, just trigger an eruption somewhere. If it's at low latitude, the right chemistry. And so if you go online, there's a wonderful movie about the prediction of this eruption. And so the U.S. had a couple of air bases in the Philippines that we were concerned about. And so they sent in USGS seismology guys who put instruments all over the volcano. And then they monitored changes in gas chemistry and seismicity and other things. And they predicted it sort of down to the hour, which kind of saved a bunch of American planes that they flew out of the air bases. It was bad news for the Filipinos. Again, a typhoon came in right after the eruption, so all this ash came down, you know, these horrible flooding events and so forth. So a modest eruption, but a very important one for us geologists to observe. Next slide. Okay, so I'm going to pick on Keith, who's going to tell my buddy Kim what I'm going to say next. So Keith is an ecologist, and I put this in just to remind you of the vision of a geologist. So out here in the boreal forest, what have I got going for me? I don't like to see this because we're having fires, but all that green stuff gets in the way, right? And so there's trees and there's shrubs and there's birds in there and moose and all kinds of things. And so to the geologists, we like 100% exposure to rocks, so we can do our job pretty well. And that's kind of hard in Minnesota, and we'll come back and talk about how you get around that with other technologies. So I've been spending 25 years of my life biking with my buddy Kim. Sorry. And it's an interesting experience because to him, when we're biking, he's naming trees and shrubs and flowers and what's invasive and what isn't, and he hears every bird and he sees every squirrel. And to me, it's just green stuff. Kim, let's talk about the Twins game or Governor Waltz doing something or COVID. And so I've been working on him to get him to see the rocks. Well, you know, to do the reverse with you, what I put up here, a brown screen, because every rock's just some brown all the stuff, and it never changes, right? Well, no. So this is my equilibrium, and so my views on ecology, my ability to identify shrub 1 from shrub 2, and an indigo bunting from a robin, it's gotten a lot better. So Keith would probably still give me a D. Kim would probably give me a D too, but I'm working at it. Anyway, so geologists, you know, green stuff gets in the way. We're interested in the stuff that's under it. I might also point out that if you have the choice to get in a vehicle to drive somewhere with an ecologist or a geologist, who would you choose? So the geologist, we're looking at every rock, and you know we're pretty average drivers, but an ecologist, especially a birder, that can be a death-defying event. All right, so I made my professional phone calls. So let's do some regional stuff, and we'll take a look at Sault Ste. Marie, the Slade Islands, Isle Royale, and then we're going to work our way kind of from Duluth up the North Shore, a little bit into Canada, and then we'll come out and talk about rocks out the Gunflint Trail and so forth. So Lake Superior, the greater basin around it, the UP and so forth, you might notice these old river systems here, glacial runoff that flowed out that way. Lake Superior used to drain out the Brule River into the Namakegan and St. Croix as isostatic things changed and the ice receded not too long ago. Big body of water, not the deepest lake, but cold and a relatively small drainage basin for a lake this big. Next slide. So my daughter put in that animation dot to make it look like I'm hip and current. I'm using PowerPoint, but I'm not at all. Anyway, that's where we are. I think the next couple of slides are Sault Ste. Marie, the Sioux, and what's interesting about that? Well, it's the connection of Lake Superior to Michigan, Huron, and why do we have a lock and dam system there? Well, we need to move a lot of stuff around, mostly iron ore going out, limestone coming in, grain going out, all kinds of things going back and forth, and water flows downhill. So this is actually the cork in the bathtub, right? By maintaining that water level to keep the Sioux locks functional, and we're able to keep ships moving back and forth, at least in the summer when it's not frozen, and that maintains the volume of water in Lake Superior, give or take. So it's around 600 feet above sea level. It's a big bathtub, but it has a cork in the end, which moves water a little bit here and there, but the net flow, of course, is down gradient out to the St. Lawrence Seaway. So the next picture is a close-up of the lock and dam system here. One of the least attractive metropolitan areas I've ever been through, but it's kind of fun to go over the big bridge, look down and see all kinds of activity with the shipping that goes on back and forth. But this has regional implications for shoreline erosion and other things relative to post-glacial rebound. But I don't think anybody would want to take that out. Next slide. So things get in and things get out, right? You've all seen this kind of stuff. These aren't my pictures, but you can find all kinds of goodies. So the sea lamprey have gotten in, invasive species, bad news for the fisheries in the upper lakes. Zebra mussels get in, and who can pronounce this word for me? Keith probably can. Q-U-A-G-G, Chik-Wauk. Thank you. So all kinds of goodies come in larval forms in the ballast of various ships from various places. Probably not much you can say about lamprey being good for anything, but how about these guys? How's the water quality of the Great Lakes since the zebra mussels got in? Patty can comment. Better. Cleaned it up, right? These are filter feeders, so the water quality is better, but does that affect the fisheries and the whole ecosystem? Yeah, it does. How do you get rid of these? Ask my wife and she'll do it. You know, here's another luskin form that's a filter feeder, cleans up the lake. So water clarity is better, water quality maybe not. Next slide. So let's go to the Slate Islands. Anybody been to the Slate Islands? Oh, a few. How, when?
We sailed up there 3 years ago.
Okay, a beautiful spot. So this is only 5 or 6 miles south of the north shore of Lake Superior. I'm trying to remember the nearest town. Can you remember the nearest? That's way east of Nipkow. Anyway, so breccia, so a geologic term, big chunks of angular things, and the whole island, the Slate Island Archipelago, it's a park, but it's an impact site. So we're going to talk about another impact site in a little bit. This one, it seems to be an Ordovician in age, so let's say 440 billion years ago, based on some radiometric things and whatnot. So you can find these amazing breccias and some other weird deformation. The next slide shows what is probably the world's biggest shatter cone. So you've got trees for scale here. So if you do experiments at the Jet Propulsion Lab, shooting things into other things at supersonic speeds, you can generate what are called shatter cones. So shatter cones always point up toward the impact point. So something hit up here going Mach 1 or Mach 5,000, who knows? But it generated this giant shatter cone. So it's in the right orientation. There's more than one. The shatter cones I'll show you in a little while for Sudbury are about this big, not building size. So this speaks towards some amazingly large bolide event that came in and impacted this place at the Ordovician. Next slide. My favorite place, Royal National Park. So there have been a number of hiking adventures in my childhood, my youth, with my family, and so forth. This is part of the Cuban Rift system. One of the first questions about Isle Royal is, why isn't it part of Canada? Why is it part of Michigan and not part of Minnesota? So I have issues with all those things. Anyway, beautiful national park, great backpacking, moose-wolf dynamic. The geology is kind of interesting. Too many mosquitoes, but no bears. So that's a nice place to backpack, especially if you're canoeing around here. You're always bringing bear bags up and whatnot. So beautiful place to go. Next slide. So hero picture. Wow, I don't look that old. Anyway, we have 3 daughters. 2 of them turned out to be geologists. And then the one in the middle is now the chemist turncoat, but we'll forgive her for that. Anyway, so we had a number of trips. We ended up on that particular trip in Rock Harbor with this amazing wall cloud that came through, and we were in a hotel room that night. So it was a miracle, and it was the boss's birthday. So it was all good. Anyway, a beautiful spot. Next slide. All right, so let's talk local. So now it looks like I'm actually organizing what I'm presenting here. So this is a geologic map of the neighborhood, and it's a nice representation of the different types of igneous rocks, for the most part, that are part of what is called the Cuban Rift system. So a rift is a term geologists use where something separates. So continental crust separating. This oceanic crust we call the ridge. So 1 billion years ago, for about a 30 million year time period, we had a rifting event that opened, lots of crazy igneous rocks and things came out. This thing you can follow with gravity magnetic data all the way to Oklahoma. So it's an enormously large extensional system generating an enormous volume of igneous rocks, and then it stopped. So we don't know why it started, we don't know why it stopped, but there it is. So the anomalous structure of a rift would be if you've been to East Africa. So East Africa is separating. So there's a continental rift system there, there's all this magnetic activity, Mount Kilimanjaro, all kinds of other crazy igneous things. That one may continue, the ocean may rush in, but this one opened for a little while and then it closed. And so all kinds of beautiful igneous rocks. If you're an igneous petrologist, this is kind of heaven because you had a mafic upwelling through Archean crust, and you end up with what's called a bimodal igneous distribution. So there are granites, and there are granophyres, and there are lamprophores, and there are Seismites, and there are salts, and there are all kinds of stuff. So all the igneous rocks are represented one way or the other. So if you, like almost everyone in here, had to have driven probably up here to take a left in Grand Marais to get out here, can't have any Canadians in the room, right? You don't allow them in yet? Anyway, I'm going to show you some pictures from up here as well. So if you start in Duluth and you come up the shore, there's the North Shore Volcanics, there's some rhyolites exposed, but most of the rocks are the brown one here, which is the Duluth Gabbro. So when you drive out from Grand Marais, you come up the hill, you don't see much exposure for a little while, and then it's pretty much Gabbro all the way to Gunflint Lake. It's kind of boring. All the rocks at Poplar Lake where I live, Duluth Gabbro, it's unfortunately really boring. But that's what we get. So a big chunk of igneous rocks, these are roughly 1 billion years old, and now we'll take a look at some of the variety of things after I talk about neuromagnetics. Very colorful, someone should make wallpaper out of this, or t-shirts, right? So the state of Minnesota has decided long ago that a good thing to do would be to spend taxpayer dollars to make an aeromagnetic and a gravity map of Minnesota. Why would you want to spend that? So what do we have as for resources in Minnesota? Over on the range, all that banded iron formation, so we're a big iron producing state, and so those rocks are pretty well exposed, but you might have more banded iron formations around the state that are either covered with all that green stuff that I don't like, or glacial deposits. So this is a way to use the technology, an airborne aeromagnetic survey. You fly a plane back and forth with a magnetometer, you make a map like this, all of a sudden you can find maybe a diamond deposit, maybe an iron deposit, resources. So the state decided that was a good thing to do. So anyway, for this image, here's the Twin Cities, Ramsey County or something probably. Anyway, the Keweenaw Rift shows up. It's all this pink running right up through the axis of Lake Superior, and all of these rocks, they're highly magnetic iron-bearing rocks. So they show up as a positive magnetic anomaly. They also show up as a gravity anomaly. So you can see where the rocks go without actually seeing the rocks. The other way you investigate rocks on the subsurface is drilling holes. Slow and very expensive. So this is a quick way to see regional geology, pick out iron deposits, all kinds of other things that are in the subsurface. All right, Hinckley, been to Hinckley? On the way to the Grand Casino maybe? And joke. Ripple marks, so there are various sedimentary rocks in these Keweenaw Rift sequences, so nice ripple marks. Next slide. If you've been down to Leif Erikson Park in Duluth, other interflow sedimentary rocks, these are beautiful cross beds, so I can tell you these rocks are upright, they haven't been flipped over. We'll see some flipped over things later, like this. These are on the east end of Lake Superior. The Jacobsville sandstone is a late rift interflow sedimentary deposit. Cross beds, but the beds are vertical. So the interesting part of geology is understanding Earth history, but in many cases, why are rocks upside down and sideways and moving this way or that way? So that's what I worry about. Structural geology. How do rocks deform? Where do they move? What do they do? So how did these rocks go from being horizontal, they're sediments, and now they're vertical? It's always a challenge. All right, next slide. We also have things that we call Pleistocene. So these are basically silty or sandy rocks that have been injected in a fluidized form into basaltic rock. So that's a type of deformation. You're mobilizing a sedimentary rock in the fluid phase, injecting it somewhere else. So fairly common up here. Next slide. We do have waterfalls that have water sometimes. So this is a gooseberry. It's not a very high flow rate. The next slide is better. This is at Magny Park. This is an interesting morphology. It's a really high flow rate, spring melt, and there's a hole down in here where if the flow is high enough, the water gets in, it self-pressurizes itself by the flow rate, and it turns into a vapor, and you get these plumes that come up. So very interesting to watch. Probably not good for swimming, unless you want to be launched, maybe as a vapor phase. All right, other goodies along Highway 61. This is right near Silver Bay. This is called the Beaver Bay Complex. These green blobs are an igneous rock called anorthosite. It's a single mineral phase, anorthite, surrounded by an igneous rock called diabase. If you walked along the harbor in Grand Marais, these big green chunks along the shore, same rock type. Used to be popular for fireplaces around here. Anyway, if you're paying attention when you go through the Silver Creek Tunnel, which is right over here, heading north, you'll notice a diabasic rock, sometimes columnar joints in it, a big fault gouge, and then you can't see this very well. This is a rhyolite that's all folded around in here. So this is a fault that's dipping to the south. It's a thrust fault. It's a neutral feature, and certainly a post-rifting fault event. You never see unless they put the tunnel in. Next slide. Okay, if you've been to Silver Bay, which we were 2 slides ago, you can drive up the road here and wiggle your way around. So you get this right, somewhere right up in here, I think. They have an overview which lets you see the delta. So what do you think of the delta at Silver Bay? Well, it's ugly, right? We don't like unnatural things that are beautiful Lake Superior setting. So this delta is the byproduct of reserve mining, processing Wasabi Range iron ore. They brought the ore down here, they processed the ore, and they dumped the waste in the lake. Perfectly legal back in the day, right? Eventually, there's a whole environmental debacle that went on that caused them to stop. The delta is still there. They're still processing the ore into taconite pellets, but their waste goes back up the hill. And you never see that. Nobody wants you to see that. Okay? These are big evaporation ponds. There are older ones other places where the deer are prancing and everybody's happy. This is inert material, it's mostly sand, silica sand. But it's an ugly spot, and when you drive through here, you see the processing plant, and all the ore sitting right here, which they then ship out in the summers. But it's a pretty hideous place. This is kind of a hallmark in environmental stuff, because this was caused to stop, and water quality was an issue. There were conversations about the waste reserve was dumping in the lake affecting water quality in Duluth, which is a long ways away, but it caused this process to stop, which is a good thing. Lots you can read about that. All right, you can also find lots of rhyolite. This is a felsic igneous rock, beautiful flow folds in here. So a dynamic eruption event. Next slide. Pahoehoe stuff, you might see this in Hawaii, and that's where that term comes from. So lava flows of a certain viscosity and composition get out, and they have these rumply flow surfaces. So that's also part of the Keweenaw Rift system. I grew up in Madison, so sometimes that sneaks in here. Next slide. This is one of my relatives. He's maybe not the sharpest tool in the shed, but he decided that he was going to haul this 20-ton copper ingot out of Lake Superior. So my family has some copper and iron mining history in our gene pool. And this guy, I'm not sure how he found this. It's only in about 20 feet of water. But in the Keweenaw Peninsula, there are unbelievable copper deposits. You can find ingots that are as big as cars. And that also brings up a problem. How do you turn a car-sized piece of copper into something that's copper piping for your house? You can't dynamite it, so you have to shred it. So go to the Seaman Mineralogy Museum in Houghton if you want to learn more about that. Anyway, my relative here did the right thing, which is the next slide. He put it in front of the mine. So 20 tons of copper times something per ounce turns into a big number, but he decided it was more important for people to see. This is the kind of copper deposits that you find. And a few of the mines are still operating over there on the Keweenaw Peninsula. Next slide. Okay, so I think this is actually Kim's picture. Many of you have gone and climbed up Carlton Peak. So Carlton Peak is a big kid word. It's called a xenolith. So it's a big blob of anorthosite which doesn't weather easily, so it's a high standing point. And this is a nice view looking off to the southwest from the top of Carlton Peak. Next slide. And here's child number 3. a turncoat who went from being a geologist to a chemist. Anyway, we went up to Eagle Mountain, highest point in Minnesota. Next slide shows the view from there. And it's the highest point in Minnesota because it's an igneous rock called a granophyre. So it's kind of like a granite. It's very, very resistant to weathering as opposed to a basalt or a diabase or an orthosite, some of the other things. So that's why it's the high point. And the rocks are deformed there too, which is an interesting observation. All right, next slide. Some of you, I'm sure all of you, have driven past the Cut Face Creek road cut just west of Grand Marais. And so, if you want, I can give you a bunch of papers to read about all this stuff. Anyway, there's a fault. These are rhyolite rocks that have been thrust up here. You can't see. There's a curved joint set that gives you the fault stance. And then there are these red sedimentary rocks, which are interflow sedimentary, sandstones and siltstones and whatnot. Beautiful outcrop. All kinds of crazy deformation detail in the red sandstones. We've dated the zircons in those with uranium lead methods and so forth. It's a fabulous outcrop. And there's a pull-off on the east side of the road if you want to get on with the rocks. Next slide. Dikes up all over the place. So the host rock here is a tonalite, Archean age, and there are all kinds of swarms of these mafic intrusions that are subvertical. So subvertical means a dike, subhorizontal means a sill, like a windowsill. Anyway, lots of dike swarms all over the place that you can take a look at. Next slide. And some of you might have gone up Mount Josephine, up near the border, which is down there. Dryden's is also down the road, Highway 61, zips right along through here. Here's an old strand line. This was this summer. It's kind of smoky, but you can see this plateau out here. And this is the top of what's called the Logan Sill, which is a rift age horizontal intrusion, which we'll see a few slides later. So beautiful view. We couldn't see it out well that particular day because it was so smoggy. Next slide. If you go a little farther north, up on the Sibley Peninsula, some beautiful road cuts of what is called the Sibley Formation. Some of these red sands and silts, but there are igneous intrusions here, the black rocks, which are silts. So these are rift age intrusions, horizontal intrusion of an igneous melt a billion years ago or so. And this is along the Trans-Canadian Highway. The next slide. I always find this interesting. This is out at Artist Point. Beautiful basalts, nicely glaciated. And it used to be a loading platform for ships going between Thunder Bay and Duluth mostly. And so I always wonder how many people other than geologists travel with a hammer and a chisel. But apparently a lot of people, because if you go and walk around out there, there's all kinds of graffiti carved into the rocks with hammers and chisels. So it used to be a common thing apparently. So we'll talk about.
Line.
Pardon me?
It's a very smooth line too, so they must have been good at it.
Yeah.
Especially for cursive.
I know.
Next slide. And we have kids that sit on water when it's frozen. She was a figure skater and a hockey player. Artist Point. And the next slide. So this has become our favorite hike. So my bride is in the back. I'm going to take a bow or not? No. All right. So we used to live east of Grand Marais before we moved to Poplar Lake. And I forget what year we did this the first time. We said, oh, let's go hike up the Gunflint Trail, and it's not very long. And then we thought, well, let's just walk up the river bit. And it was August, low flow, a dry year. And so you go up, I think it's 9 waterfalls up to the point where you can get to the Superior Hiking Trail Bridge. And the first time was a little dicey. Subsequent times we brought a rope just because we're old and feeble. But it's really fun. Huh?
We did not use the rope.
We didn't use the rope, but I did drop the camera in the river and she found it later. So anyway, amazing canyon. The canyon depth is over 400 feet from bottom to top. So if you walk the trail, you're looking, oh, it's down there 10 feet. Well, if you're at the bottom looking up, it's like, how the hell am I going to get out of here? But climbing up those waterfalls was really fun. And the geology, it turns out there's some really interesting things in here, some deformation in some of the rift rocks that I was unaware of. So beautiful hike if you can do it. You've all seen agates, right? So these are one of the mysteries of the earth. You find agates in basaltic rocks, which are vesicular. So they crystallize in a way they have little spheroidal openings. Sometime after the country rock crystallizes, you have to have a vapor phase crack find its way in there to form the outermost layer of the agate, and then another phase has to puncture that to do the next. So you're filling these from the outside in. And then you get some really crazy cross growth patterns. So most of the mineralization that forms what you then call an agate is quartz. It has different impurities in it, so you have different colors. But you also find zeolite minerals in there, all kinds of other crazy things. So these are secondary features that are filling vesicle voids in a basalt that's 1 billion years old. And then your question would be, well, when did you fill them? Was it last week, or was it a billion years minus 1 year? Probably it's 1 billion years ago-ish. But nobody's figured that out yet. You can't date quartz. Anyway, agates are part of the story up here. Next slide. Amethyst, another one, right? So most of the action for amethyst collecting is up east of Thunder Bay. There are a number of big quartz veins that have been discovered many years ago. And the color, the purple, is radiation damage to iron. That's an impurity in the quartz. And then there are secondary minerals in here. These are zeolite minerals that are not the purple ones. But you can go up to a bunch of these places. They're kind of mom and pop quarries. They have dynamite permits, so they blow stuff up every once in a while. You can go observe that as well. And then you can be the first person to pick over things. And you pay by the pound or the ton, whatever you want, that kind of stuff. So this is a rift-related phenomena that I think a lot of people have fun with. And, next slide. And of course we have these guys. So this was a picture I found online. I should give the sales pitch of your presentation, Keith, with your pictures. But anyway, we've had a couple of loon families on poplar this summer. Anyway, Scazophon, the Minnesota state bird. Next slide. All right, so let's do some more geology stuff, and then we'll go up the Gunflint Trail for Grand Marais after a couple of these slides. So these are our fancy statewide representations of geophysical data. So we can use a gravity base and a magnetic base, and we can combine those two different geophysical methods to make different maps of the state. And what do you see? Well, here's the Chik-Wauk rift stuff. Up and around. This has a very distinctive signature. All of this is rift rocks. And then when you get out into here, you're seeing through trees and all that green stuff. You're also seeing through soil. You're seeing through all the glacial deposits. And in some cases in southern Minnesota, you're seeing through the Paleozoic sediments. And you start to pick out different patterns. And even though the rocks aren't exposed in most places, well, that looks interesting. Let's drill a hole in that and see what we get. Or maybe that looks interesting. Let's drill a hole in that. Or maybe you see these sets of linear features here. These are mafic dike swarms. Here's a big fold. So all kinds of other things show up. This is funded again with state tax dollars because there's a resource angle to it. Let's find another band of iron formation. Let's select the Wasabi. Let's find a diamond deposit. Let's find a gold deposit, a nickel deposit, whatever. So for a structural geologist doing tectonic things, these are also really valuable for understanding regional features between the Chik-Wauk rift system and all this other Archean stuff and so forth. So the next two slides are kind of like the opening slide. So with all of that in mind, fieldwork, drilling, gravity magnetic surveys, you can delineate out different groupings of Archean rocks. So again, Archean means anything 2.5 billion or older. So most of Minnesota is made up of really old stuff. And there's other old stuff under here with younger Paleozoic stuff on top, as well as the rift rocks. So we're going to end up talking about where we are up here, and those are Wawa rocks. Wow, the Wawa rocks. Well, the Wawa province also includes Wawa, Ontario. Anybody been there? And?
It's rocky.
Thumbs up, thumbs down. It's not much of a town.
There's a Tim's there.
There's a what?
Tim Hortons.
Oh, there's a good one. Yeah, well, I don't know if that's is that an upgrade? I don't know. So this is the modern view of subsurface Minnesota. Parts of the boundary waters and northern Minnesota are part of the Canadian Shield, meaning whatever rocks were on top of these rocks have been scraped off by glaciers so we can actually see them. So again, look, here's a nice fold in cemented sedimentary rocks in the Craddock province. And so this ends up being part of that grander Canadian Shield, and it's becoming better and better understood. So lots of radiometric ages. Most of these are done by this kid. So Mark Schmitz grew up right there in a nameless, tiny little Minnesota town, and he came to Macalester and then has been is just a remarkable geologist, geochronologist, dating all kinds of stuff. So, okay, next slide. Another view of the state, different fault boundaries in yellow, and then all kinds of different terrain boundaries and this, that, and the other. And again, you can't do this without the gravity magnetics, some drill data, and then lots of good mapping. And so you might also recognize that as the Wasabi Range. So a abandoned iron formation that dips to the southeast and it underlies this whole region. You're never going to run out of that ore, ever. Huge amounts. And where does that deposit go? Well, it shows up at Gunflint Lake, right there. You can follow it over to Thunder Bay. It underlies all of these igneous rocks, and it disappears up in that part of the boundary waters. All right, next slide. So Minnesota relative to the Canadian Shield. So over the years, we've been able to delineate all of these different terrain boundaries that make up the Canadian Shield, called the Superior Province. And so these rocks are 2.7 billion years old. They young all the way down to here to 2.6 billion years.
It's okay.
Okay, all right. So this is a huge piece of oceanic crust made up primarily of that tonalite word, and all of that formed in 100 billion years, which is not a lot of time, geologically speaking. All right? And so again, here we are in the Wawa terrain. And next slide. I feel like I need to talk faster because I'm running out of battery. Okay, so let's go local. We'll start in town and then we'll come out the trail. So here's one of my favorite words, tombolo. So a tombolo is a bit of rock, artist point, connected to the land with a pile of gravel. And so Grand Marais means what? Big swamp, right? From French, the French translation. And let's see. There's Biz's yacht, right? So, the harbor and town. And so let's go places from there. Next slide. Maple syruping. So my maple syrupers are not here. The Spindlers run the northernmost maple syruping operation in North America. And if you try their syrup, it's not available at the co-op or Jeans or many other places, so you have to go to their house and get it. Anyway, I helped them do some syruping. It's just north of town. Next slide. You've all seen these, right? Beautiful but invasive. Lupine. Next slide. And you're all up here to do this. Get away from it all. And next slide. So this is one of the great mysteries to me. If you go in the boundary waters and you go in 6 lakes, and then you come across this. And so when I go from lake to lake, I pick up the boat and I carry it, right? That's called portaging. So what does this tell you? Hundreds of people are dragging their aluminum canoes from this lake to the next lake. It's horrifying. So these are called striations. So geologists get interested in those because they're related to faults. So we see canoe striations, not to be confused with the next one. Snowmobile striations. Right? And these are in different places because they're on different trails and they're not on portages. So again, if you're on your snowmobile going 30 miles an hour and you see a rock, let's hit it. So it's steel on rock, the rock loses, but you find all these weird striation things in the weirdest places. Next slide. All right, so we're talking about striations. Glaciers leave striations. Glaciers polish off and round off everything. So here's the world maybe 14,000 years ago. So the big ice cap that grew over Hudson Bay, it grew outward from there, kind of ran into Greenland and Baffin Bay, so it had to grow somewhere else, kind of grew this way. Eventually it ran into the Canadian Rockies, and then the only other place to go was south. So you're accumulating snow, and that's not my phone, all right? So for the Laurentide ice event, or the Pleistocene ice age, it started about 2.4 million years ago. There are all kinds of little advanced retreat events superimposed or second order to 4 big advances relative to the ice in the lower 48. So there are 4 different phases. We don't have to worry about all that. But anyway, ice came moving down, scoured out the Great Lakes, and left all kinds of glacial landforms all over the place. And that's what we're left with when the ice receded, meaning the ice melted. It stopped accumulating, it was in a disequilibrium and all that ice started melting. So this went away. The remnant is what's in Greenland, and various other valley glaciers in the Cordillera, and so forth. So a lot of the landform evolution that you see around here is the result of glacial advances over that 2.5 million year period. So the next slide kind of shows you the same thing. So a better representation of the Great Lakes. And so again, water flows out this way to the St. Lawrence Seaway. And this is 10.5 million years, sorry, 1,000 years ago, so 10,000 years ago. So again, as geologists, we think in billions and hundreds of millions of years. This was last weekend, right? 10,000 years ago, so, you know, it's only a few generations ago you were under 1,000 feet of ice right here. And it has since disappeared. A lot of that water filled up what we now have as lakes everywhere in this part of the world. And it's a very, very recent feature. So glaciation was recent, the ice retreat was very recent. And what did humans do when the ice retreated? We filled into those environments, right? In Europe, all over North America, Asia, and so forth. It's a whole new environment. All kinds of other organisms moved into those things, and we're left with this relatively modern glacial series of landforms. All right, so the next slide. Okay, so if we keep coming up the Gunflint Trail out toward the trails in here, this is over on Clearwater Lake. So I think now that this might be a fen. I'm thinking I can ask Keith that question. What do you think? Some kind of upwelling? I mean, Clearwater is so clear. Maybe there's some fens feeding that. Anyway, this is up on top of the Palisades. So this is the Logan Sill. They're beautiful columnar joints here. The rose slates are down below. So a lot of people who live along these lakes have access to the road formation. So they have slate walkways, living rooms, all kinds, because it's the rock that's available, right? And if you're on top of this palisade, it's also been glaciated. It's polished bright, polished off. So you're way up high, means the ice was even thousands of feet higher, and mostly moving parallel to these lakes, parallel to these troughs. Okay, so something nice, it's a nice paddle on lake over there. Next slide. If you go down the Clearwater Road, there's a gravel quarry, and this is what we call a cave deposit. So if you don't want to go to Thorson's and buy class 5 gravel, where's Mark? You can go down here with your bucket and shovel, and you get some pretty nicely sorted stuff. If you look to your left, next slide, it's faulted. This was a surprise to me. So this is last week's glacial gravel, but there's a fault. I think this unit used to be connected to that unit, so this went like that. I don't know why. There's no tectonic reason for that, but it's an observation of deformation in a modern deposit. Across and around the corner, the next slide, you can find the remnants of an esker. So these are nice because they have a different sorting. There's sand, there's gravel, there's boulders. So if you want one or the other of those, it's not too big of an effort to find the bits and pieces that you want for your various projects at home. So nice glacial deposits. Next slide. If you take a hike around the Gunflint Iron Formation, the Gunflint Formation, which is a banded iron formation, you can see some beautiful stromatolites. So these are old algal communities, and so they grow upward toward the sun in a marine environment. You can find modern examples of this at Shark Bay in Western Australia and so forth. So let's see, the next slide shows my towering, enormously strong life next to magnetic rock, right? So I know she pushed it up, right? She's not smiling, maybe. So many of you hiked out here. So this is an iron formation, but it was deposited horizontally, and now it's vertical. How did it get there? So you have some choices, right? Aliens, maybe, or they're Canada, maybe one of them came over, I don't know. Maybe the moose pushed it up. So the logical choice is this was horizontal, it was plucked by a glacier and rotated up. So you can see these fairly commonly in many glacial environments. So it's a beautiful monolith. I think of HAL, Space Odyssey 2001, right? Anyway, beautiful spot. So maybe it'll tip over one day, maybe it won't. So the iron formation here, which is found along Gunflint Lake, the Gunflint Formation, it's an iron formation. These are the exact same rocks as you find in the Wasabi Range. They just had a different, about different post-depositional history and the mines that were opened for, I think, an hour at Paulson. There's a nice display in the museum here about the Paulson mines. Brought in a railroad from Thunder Bay. They had a few little pits here and there. They took a load of ore out, and then they decided that all of the iron in this particular iron formation was in silicate form. So it's Fe plus SiO and a bunch of other stuff. So if you go over to the Wasabi range, it's Fe2O3 or Fe3O4, hematite or magnetite. How do you separate the oxygen from the iron? You just heat it up. How do you separate the iron from the silicate? You quit, because it's not economic. So there's a very different post-depositional deformational history here. Even though this has a lot of iron in it, it's in a silicate form and you can't get it out cheaply. So they quit, and that was a good choice. So that allowed us to not have a bunch of mine pits over here when we put in the boundary waters and so forth. So that has an interesting history. Next slide. We had black ice this winter, and on Poplar Lake we had black ice with a beautiful sunset, but it wasn't skatable. And then we went over to another lake. Next slide. We ran into somebody funny. You're supposed to gasp. A funny lady with a dog that's a lowrider. And I don't see my buddy here today. Anyway, this is my neighbor. So this is over on the public access on Loon Lake. We were a little bit post-peak because it had snowed a little bit, but you could still skate for miles and miles and miles and miles. We went out to Seagull. Anyway, it was a beautiful freeze event early in the winter, and skiing was quite wonderful. Anyway, next slide. So we have other events that happen out here. So turns out in 1999 we were here on vacation the week after the blowdown, and we heard about it and we came anyway. And then why are all these chainsaws cutting these trees on the highway? What's going on? Anyway, it's a very interesting thing to see. So some of you were here during this blowdown event from west to east, straight line winds, just flattening huge amounts of the forest, and a very devastating event. And then this, of course, led to the next slide. So the blowdown, but also then the fire. So the Ham Lake fire, next slide, did something like this. So if I remember right, it started here, it went that way, then it went this way, and then across the border, and it came back around. Here's Poplar Lake, where I live now. Very devastating. And so just out of randomness, we also came on vacation to go canoeing like a week or a month after the Ham Lake fire. And we read about it, and we had this trip planned, and well, let's go anyway. So it was an interesting experience to see everything just burned across the region. That, of course, was an opportunity for geologists because, again, that green stuff went away, and you can see all the rocks. So a lot of geologists got in here a few years after the Ham Lake fire to be able to map and figure out the geology that had been mapped first in the 1880s and then various other iterations over the years. So something good came out of that. Next slide. So this is from Keith. There are cedar trees around here. I think these are on the 200 to 300-year-old age range. There are a few out on an island in Seagull that are described in the Gunflint Burning book by, I forget the biologist that worked on that. Yeah. Anyway, it's a nice write-up of these really old trees that survived the Grand Lake fire and other fires and are still going. So there are trees in different parts of smelters, and the wind blows from northwest to southeast. So downwind of Sudbury, everything has birch trees that are this big, and there's just smudge on everything. It's a horrible place. It's not as bad as it used to be, because they now use scrubbers on the smelters. Anyway, so this impact event caused 480 miles away a disruption in the sedimentary basin that had the Gunflint Formation in it, and there's all kinds of crazy breccias and other goofy things that are the result of that. So it was an impact event, a seismic event, a tsunami event, and hundreds and hundreds of miles away. So what's your other favorite impact? So everybody's pro-dinosaur, right? The Cretaceous Tertiary boundary, so somewhere down in the Yucatan is where that impact was. So it's of comparable size in terms of the asteroid. It came in about 10-fold faster than this impact, and it came in vertically, not at an angle. So the outcome was different. And then, do you miss the dinosaurs? Do you care? Anyway, so during my career, the discovery of that impact site and then also the change globally from that one event in sedimentary systems and global extinctions of foraminifera and all this other kind of stuff is really been well understood. So this is a follower to understanding the KT impact site, and now we have a better understanding. So I think I'll show a bunch of field pictures next. Yeah, so here's some shatter cones. You might remember from the Slate Islands, shatter cones were as big as a building. You know, these are little guys. But this is right at the impact layer, and this is found everywhere around the Sudbury impact. Next slide. You can also find melted rocks. So this is a big kid word. Pseudo means fake, tacolite means glass. But this was a melted rock that resulted from the impact. So it's glass that then crystallized out, but it has brecciated chunks in it. Next slide. You can also find what are called lapilli. So if you have an impact event, stuff becomes airborne. It might get wet, flies around, eventually settles out. So these are nicely spheroidal features. There's a subsequent deformation of it. So all these are little ellipsoids now. They've been deformed. But these are ashfall. It's ash fallout from that impact site. This is a couple hundred miles away. Next slide. You can find rocks that we call Tsunamites. This is a tonalite. This was some sediment that was in the neighborhood. But you ran that seismic energy through this and it liquefied everything. So it's a very chaotic sedimentary eruption. Next slide. And then one of the best exposures of the contact is kind of west of Gunflint Lake, a few miles, not too far from Magnetic Rock. Beautiful folding patterns. And then the next slide shows this in profile. So this is the Gunflint Iron Formation. It's all folded around. And then right on the top, which is the next slide, you find these lapilli. So this fell out of the sky onto a breccia. And that was the end, globally, of the deposition of banded iron formations. So one of the revelations from understanding the Sudbury event is the world was going along doing its thing. You drop one rock in, and it changes the entire ocean chemistry. So the next slide, the breccia, go ahead, it's okay, go to the next one. So you can find this brecciated Gunflint Formation, all kinds of places, including in the fireplace at Gunflint Lodge. And then the next slide shows the change in ocean chemistry and deposition as a result of that one impact. So this means giga-animated. 1.85 billion years ago, you throw one rock into the surface, it stops the deposition of these iron formations, and the only other kind you find are the younger ones that have almost no iron in them at all. So the world changed on one day when you have this impact event and the superior type banded iron formations stop being deposited. So it's a very strange thing to have one 10-kilometer chunk of rock come in, changes the whole ocean chemistry. But that seems to be the story. All right, next slide. All right, so again, we'll come back and talk about the Wawa stuff, and that's where we are. Next slide. So I think this might be your foundation. So Dave Towle was working at our house, and he said, Craddock, I need you to come out and look at this basement foundation that I'm working on. So this is out along Seagull, and he gave me the name Landy. Anyway, he said, well, there's something unusual here. And so I drove out and looked at it. So anyway, this is the Sag Tonalite, 2.6 billion year old igneous rock. And there's a little quartz zone that's kind of a fault in here. And it's been inactive for probably 2.5 billion years. But it was an interesting exposure just to see what the Sag Tonalite looked like in a fresh surface. So, very common rock out here. Next slide. And also, you can find west of here a tonalite, but it has shear zones in it. So I'm a structural geologist. I'm interested in when was this fault active, what was the sense of motion along this fault, and I'm still working on that. And I'm hoping for some radiometric ages and some surprises there. Next slide. You also find beautiful dike swarms out here cross-cutting the Sag Tonalite. This is a lamprophere. It's about 2.01 billion years old, based on the ages we have on that. It's part of a bigger dike swarm. Next slide. You can also find pillow basalts. So these are found in modern environments. If you go to Hawaii and watch the lava go into the ocean, you find these tubes of lava. They have a rim around them, so the curved side is up, the attenuated side is down. This is not particularly deformed, but in the next slide, you can see pillows that were that shape that have now been completely deformed. And so again, these are Archean lavas that have been deformed subsequently by tectonics deforming the lava rocks. Next slide. Also some crazy folds. Next slide. Other crazy folds in banded iron formations. And other crazy folds in turbidites. So these are called eye folds. So this layer, coarse grain layer, connects three-dimensionally into this one. So it's a doubly deformed conical fold, blah, blah, blah. Anyway, beautiful stuff. Next slide. You can also find along plate boundaries, so between the Wawa terrain and the Quetico terrain, there are thin little seams of glass. So again, we use the word fake glass. But this is the result of motion along that plate boundary that causes the rock to melt along the fault. So it's a supersonic motion causing instability in those silicate minerals, and you get little injections of fake glass. And you can actually date these radiometrically. So beautiful stuff if you pay attention to it. Next slide. So the Wawa terrain, if we go back a bunch of slides, these are Archean rocks, lots of tonalite, some rhyolite, some basalt, some chromatites, and other things. And if you've been to Coldwell, Ontario, along the Trans-Canadian Highway, the Hemlo Gold District is there. And it's about 6 feet from the highway. So you think of the expanses of Greater Ontario and the Canadian Shield, and one of the most prolific gold deposits anywhere in all of that wilderness was 6 feet from the highway. And it's an amazing place. Anyway, that's the sign to go in there. I think there are 3 working mines at the moment. I've been out there a while. Unbelievable quantities of gold in these Archean rocks. Well, why do you care? Those same rocks are right here. So this is the Wawa terrain, right? So are we going to have gold mines in the boundary waters? Not likely. There was a gold mine that operated, I think, in the 1860s and 70s called the American Mine. It was kind of near International Falls. Same rock types. So the mineralization is there. Archean rocks around the world contain most of the world's gold deposits. And they also contain most of the world's kimberlite deposits, which is a whole other story about some younger kinds of intrusions. Anybody know what goes on in a kimberlite? Diamonds, thank you. Yeah, so kimberlites are mantle intrusions that come up at supersonic speeds. You can argue that because a diamond is only stable at high pressures and temperatures, for it to get from 200 kilometers down to the surface, it has to do that in a really short amount of time. So it's an amazingly dynamic eruption. So, anyway, Yellow Brick Road, Wawa terrain is loaded with mineralization, both in Canada and in the US. Next slide. And I've been working on some rocks west of here, so I had to put in the word Diamictite because it's in the title. This is a type of sedimentary deposit. It's vertically oriented. All kinds of interesting clasts that are probably sag tonalite, and some faceted things. There might be a few drop stones here and there. And so we're working on, well, maybe this is a glacial deposit that hasn't been recorded in Earth history. Was it local? Was it regional? And we're trying to figure that out. So stay tuned, and there's still a few more slides. Other beautiful polydictic conglomerates are found out in these Archean terrains. There are chunks of banded iron formation in here, the reds, sometimes some cherts, and other things. And the next slide, other wonderful folding and faulting relationships in some of these older local iron formations. So this is the Sudan Formation over by Ely, once one of the most prolific iron mines that went underground after a while, supplied iron to the Union in the Civil War, and was important in other military adventures in this country. So next slide, yeah, the end. So Bullwinkle, he's everywhere, right? All right, thank you. I really like this room because of that.
What?
The moon.
Oh.
Yeah. So let's see, there's a really long answer that I can share with you some other time. So it's a mechanical conundrum. You have the sag tonalite, 2.5 billion years old. It's 30, 40 kilometers thick. Somewhere below that, you have to have a magmatic melt. It's a romantic composition that has to come up, force its way up. So it's something old and thick and strong that has to separate to let that material come up. And when you find one dike, they're usually in swarms, but they're also long. So it's not a mile long, it's 200 kilometers long. So again, how do you force a weak liquid to come up through something thick and old and cold and go sideways 200 kilometers? Or it might just come up and feed a lava flow. Or it might do both. So I don't know. But I could ramble on for hours about it. Anyway, but they're very common features. Go ahead.
Yes, hi. What would happen if we didn't lock the Sault Marine locks?
Well, Lake Superior
Given
would
that these rebound things and.
push the water out. So you lose volume, and then you can't ship anything.
Yeah, but what would it look like? Would it a lot more water there, or?
No, Lake Superior would drain, and then it would be isolated until it,
okay.
like spring melt, it might get high enough to go over the lip.
Oh.
So you have to maintain. The Sioux maintains the water volume of Superior. So you have to
Okay.
maintain, but at the same
So
time.
if you put those locks in there, like Lake Superior could be.
Oh yeah, it'd be way lower. Yep.
Wow.
Yeah. And so who wins? So if you're tipping the bathtub, I don't know, that's north, right? So if you're tipping the bathtub, Hudson Bay is rebounding up, who wins? Canada wins, right? They get more beach, and what do we get on the South Shore? You're tipping the bathtub to the south, it's plugged over here at the Sioux, so you get erosion on the southern shore. So here's your next political platform, right? Canada's winning and we're losing relative to shorelines in the Great Lakes. But we like the Canadians, right? Trying to work things out with them. We don't want them in right now. But, yeah.
Can you tell us a bit about the greenstone that we have around here?
The greenstone, yeah, it's kind of a poorly named rock. So a rock that's green, what does that mean? Well, so for the most part, in the Archean, you have what are called granite greenstone belts. So granite is actually a poor choice too, because most of the granites are tonalite in the Archean. And then the greenstone is basalt, but it's been metamorphosed. So the green is the mineral chlorite, usually, and sometimes the mineral actinolite, which are greenish silicates. So a couple of the slides I showed, if you want to go back like 3 or 4 slides to those, keep going, maybe 2 more, keep going, sorry, keep going, this one. So that, you would call that a greenstone. So it's a basalt, this happens to have pillow structures in it, but that looks kind of green. Yeah. So there's chloride and actinolite in that, which is a metamorphic overgrowth mineral, so it looks green. So they sort of get blanketed in greenstone. Well, it's still all basalt, it just has secondary metamorphic minerals that are chloride and actinolite, and sometimes epidote. So it gets a greenstone. So it's kind of down, but that's what we've done.
I have a follow-up question then. I read that it's associated with the iron formation along the Mesabi to the Gunflint. That the greenstone kind of follows the.
Yeah, I mean that you can't draw across it. So if you go to the Mesabi range, rocks like this underlie the deposition in the Inimiki Basin, which was initially a quartzite, a kegel quartzite, and then above that is the Virginia slate, some places, but then it's banded iron formation on top of that. So the contact is depositional, so the Mesabi iron range formation names, or whichever names you want to use, it's in depositional contact with these rocks, which are deeper and older. So it's an unconformable contact in most places. Yeah. Keith,
I have a question about green stuff.
about what?
Green stuff.
Green stuff.
Yeah, green stuff,
They're
okay?
going to call me out.
Yeah.
So I can take the fifth right off here.
Okay, you showed a picture of Craddock, which are the first green stuff on the planet, like 2 billion years ago.
Right.
What role did they play in the Iron Banded Formation?
Probably none. So there are Tonalites that are much older in Earth history. So they're sort of the cornerstone for oxygenating the ocean, which led to oxygenating the atmosphere.
And oxidizing iron in what was formerly free floating in the seas? And then I'm just wondering if there's a relationship between the oxygen and the oxidation of the iron and our Iron Range Formation.
Well, so I'll take the easy way out. So I'll say no. But if you look at the mineralogy of even the whole Mesabi range, there are places where you find iron oxide, hematite, or magnetite, or sometimes ilmenite even, as a primary mineral. There are other places where you find iron as a carbonate, siderite, and sometimes it's even in other goofier things that aren't silicates. So there are examples throughout the Mesabi depositional system of iron bonding with oxygen, silicon, carbon. And so maybe the better question is, where does the iron come from? So it's seemingly eroding off some continent somewhere, or being re-injected into the water column through mid-ocean ridge system, which you see in the modern world, these black smoker fields or something. So there's all kinds of recirculation of metals out of basaltic rock, and it might be both of those. So the iron mineralogy and all the banded iron formations is really complicated. So, and then maybe the other way to answer the question is, if you're interested in extracting the iron from a banded iron formation, all you care about is the oxides, because all you have to do is heat them up. So you separate the iron from the oxygen, and that's easy. So you kind of ignore the siderite. You can't do anything with the silicates because it's too hard to separate them out. But that mineralogy is really complicated. And then you drop the Sudbury impact in, and it stopped forever. Yeah.
The Sudbury impact, the ejecta, what does that consist of? And is that where the iron came from, or the iron already there and the ejecta went on top of it?
So the impact asteroid might have been nickel rich. There are nickel meteorites, so that might have been the source of the nickel that ends up being mined in Sudbury. It has nothing to do with the pre-existing iron deposition.
Okay.
So for whatever reason, that impact changed water chemistry, maybe atmospheric chemistry, and so whatever the source of iron was changed that day, and there was no more banded iron deposition after that. So the ejecta, part of what you see are those little lapilli I showed. So there's all kinds of stuff that went up into the atmosphere and settled out. Sometimes these little spheroidal balls, there are breccia chunks, so really weird things all over the place. There are shocked quartz grains, shocked zircon crystals, and so it's a really complicated breccia layer that's the ejecta, plus the ashfall stuff that settled out after that. So go to Sudbury. Yeah.
I missed the first part of your presentation, so you may have already covered this, but you get a big map of the Gunflint Trail, just look at the shape of the lakes. And after traveling around, you notice that north of the Gunflint, birch mayhew, etc., they tend to be long and linear. You go south of the Gunflint, Poplar Lake, Fairwood, etc., rounder, shallower, darker water, a lot of islands. And then you go to the, Gunflint magnetic narrows, and then it changes too to the Tonalite.
Yeah.
I mean, how many some areas are they like that there? And do you know the order in which they occurred?
Well, so the simple answer is across the border it's tonalite. So the Gunflint is a trough separating tonalite that's dipping south from banded iron formation, row formation, Duluth Gabbro. So everything in the rip dips south or east. So that pre-existing depositional fabric kind of delineates where the ice flowed and scoured out things parallel to that. So north, it's all kind of lumpy. Once you get into the Chik-Wauk system, things tend to be somewhat more linear in some places, but it all depends on the layering and then the composition of the rocks that are there.
No simple answer to that.
Pardon?
No simple answer then.
No, not really.